This is a typical vertical box plot. This is a horizontal box plot. This is a box plot with a wedge, a box plot with the categories, and this is the box plot with categories inside categories. You might have come across some type of box plots before, but have you ever wondered what these box plots actually could represent, or how could we interpret these box plots? Let us understand in this video. For that matter, we need to look at how these box plots are plotted. Consider a scenario where we have passengers traveling in a train. Now, some volunteer took note of the age of all these passengers and plotted them on a single line. So, this is a single dimensional problem. Now, in order to start plotting the box plot, the first thing that we need to find is the median. The median is the center point in my whole distribution. Now, in our case, we had 20 passengers in total. If the number of passengers are odd, we can simply find out the center point using this formula. But if the passengers are even, which is in our case, we couldn't find a single center point in our distribution, and that's why we have to use the average of my n by 2 and n by 2 plus 1th point, which in our case is a 10th and 11th data point. So it would be the average of 10th and 11th data point, which is the 10.5. Now once we have found out the median, the next thing that we need to find out is the 25th and 75th percentile. If I say 25th percentile, that simply means that 25% of whole data, which is 5 data points in our case, are below this particular data point, including that data point. So this is my 25th percentile. Or in other words, I can say if I select a random passenger in the train, the probability of his or her age being between the minimum age in the train and this 25th percentile data point is 0.25. Similarly, we can find the 75th percentile. Now, once we have these two data points, which is the 25th and 75th percentile, we can use them as a boundary for our box. Now, half of our work is done. The next half is to plot the whiskers. Whiskers are nothing but the lines that extend from the box on both the left and right hand side of the box. Now, the only question that remains is what should be the length of these whiskers? Because the endpoints of these lines represent the minimum and maximum value that my distribution could have. Now, ideally, I could have extended the whisker length up till my minimum and maximum data point that we have observed. But in real world, it may happen that some of the data points do not represent our original distribution. For example, consider the case when volunteer, while taking note of the age of the passengers, did a typo and instead of writing 20, wrote 200 as the age. And until this date, when I'm making this video, we know that it is not possible to achieve that age for a human being. And that's why it should not be considered in our distribution. That's an outlier. And because of these outliers, to represent our distribution correctly, we should avoid extending our whisker lengths up till the minimum and maximum data point in our observation. Instead, we use this box length, which is the distance between Q3 and Q1 data point, also called the interquartile range. Now we multiply this length by some factor to get our whisker length. In the original definition, this factor is 1.5, which is defined by Tukey, who actually invented the box plots. Now you can change this factor as per your scenario. So the overall idea is that the whisker length should be this factor multiplied by interquartile range or the minimum or maximum data point, whichever is smaller. Great. Now you understand how you can construct a box plot from any given data. And so it becomes really easy for us to interpret the box plots to get the idea of data distribution. First thing first, a box plot is used to summarize the data distribution using 5 numbers. If you are into statistics, you would have often heard about the term 5-number summary. Now these 5 numbers include the minimum data point that we have in our distribution, the first quartile, which is the 25th percentile data point, the second quartile, which is the median, the third quartile, which is the 75th percentile data point, and the maximum data point in our distribution. These 5 values are used to summarize our distribution, and hence the name 5-number summary. By now, you would have also got the idea that box plots could be used to detect the outliers. So any data point which is not in between this minimum and maximum value is either the outlier or an suspected outlier. But you should keep in mind, although the box plots are used to detect outliers, they will not always detect an outlier. For example, consider our train scenario itself. So while noting down the age of a 1-year-old boy, the volunteer did a typo and wrote -1 instead of 1. Now, clearly we know -1 is not the part of our distribution and hence an outlier. But since the distance between 1 and -1 is not that much, -1 is also included as a part of our distribution and is not detected as an outlier. So remember, box plots can detect outliers, but not all of them. So the next thing, if you have observed that the distance between Q3 and Q1, which is also the box length, contains 50% of our whole data set, and the rest 50% lies along the whiskers. So that simply means if you have a very short box length, that means that the data is very tightly packed in that particular area, and you can focus more on that region as compared to other region. But if you have a larger box length, that simply means that the data is very well distributed along the whole range. So shorter the box length, tighter is our data distribution. Now the last thing to note is that box plots are also used to check if the data is symmetric or asymmetric, and if asymmetric, up to what extent. Now the perfect example for a symmetric distribution is a normal distribution, where all the values on the left hand side of the mean are mirrored on the right hand side as well. But in an asymmetric distribution, the values are not mirrored, and hence you can see a long tail either on the left or the right hand side of my mean value. And based on the direction in which the tail is formed, there are two types of asymmetric distribution. One is positively skewed and another is negatively skewed. And these are the box plots for them. Now skewness is used to measure the amount of asymmetry in my distribution. If a data is positively skewed, that means there will be a tail on the right hand side of my distribution, and that simply means that most of our data will be sampled on the lower side or the left hand side of the distribution and not from the right hand side. And that can also be identified in box plots if the distance between the median and the first quartile is less than the distance between the median and the third quartile, then it would be a positively skewed distribution, and vice versa for the negatively skewed distribution as well. But why do we want to learn about skewness at first? If you observe the positively skewed distribution, you can see most of the data points are on the left or the lower side of our scale. And that gives us an idea that most of our suspected outliers will be in the right hand side where we have lesser number of data points. And if we are using this data for building a machine learning model, and since most of our data points are sampled from the left hand side, the machine learning model will predict better results on the left hand side of the distribution as compared on the right hand side values. And that is why we must be aware about the skewness in our data distribution, where box plots can be used as a simple visualization tool to measure this skewness. So these were some of the observations that you must keep in mind while dealing with the box plots, which will help you becoming a better analyst at your job. As a next step forward, you can also try generating your own plots in Python through my other videos in this playlist. Thank you for watching.